how did they come up with this equation? And let's derive this equation. But what does it look like? It looks like it's a variation, a form of the Newton's second law, which says the sum of the force is equal to the mass times acceleration. It sure does. Sum of the force is equal to the mass times acceleration. They have a minus sign right here. I wish they would have put the minus sign there and kept it off of there. Would it be any different if they put the minus sign in front of the gradient p? No. And if you have a coordinate system that is x, y, and z is going up, and often we put gravity going down, true, like that. Which direction is g as a vector? G as a vector is 0i plus 0j plus something k. What is it? What's something? Positive g or negative g?
Negative.
It is negative g. So that makes a whole lot of sense because you would have a minus sign in front of this g, k. What is k? Unit vector in the direction of positive z. What's I? Unit vector. These unit vectors, right? Unit vectors. That's a vector equation. This whole equation up here is a vector equation, true? So that equation comes from sum of the forces equal mass times acceleration. We'll derive it. And then we interpret this term. This sure does look like the force due to gravity. This is a vector equation, true? Every term is a vector. This acceleration is a vector. It's A is equal to AXI plus AYJ plus AZK. So now I look at that first term minus del P. Minus del P. What? So it's the gradient. Sometimes I'll write it like this. Grad of P. Gradient of P. If I have the operator called the gradient operator, what does it apply to? Does it apply to a scalar field or a vector field? And what's the difference between the two? All right, okay, well, what do you mean by a field? Meaning somewhere in our domain, a lot of times it's easy to visualize in 2D, x, y, but it's true in 3D, x, y, z, but it's hard to visualize in 3D sometimes. You have a field anywhere in any combination of x and y. You can go to that location and you can inquire or draw back some information. Right? That's what we're talking about, field. So what do you think is available for information at every point in the field if it's a scalar field? Just a number. Now it has units associated with it, but it's a number, a magnitude. And a vector, magnitude and direction, magnitude orientation. Three-dimensional entity in the Cartesian, x, y, z, versus a one-dimensional entity, so a scalar field. So what do we feed the gradient here? I feed it, I know I'm feeding it pressure, but is pressure a scalar field or a vector field? So you feed the gradient operator a scalar field. I didn't say scalar like a number. No, it's a number at any point x and y. It's a function of x and y. Sometimes we can't get it analytically. Sometimes they make up a nice analytic equation for the pressure or some other scalar field. Now, once I have that scalar field, I grab it, I do the gradient operator on it, and the result gives me back a vector field. So this is a vector field. So this is a vector entity, vector entity, vector entity. Let's sketch out the pressure field maybe as a function of x and y so I can visualize it. Just make it 2D. Maybe the pressure, I have contours of constant pressure that look like this. Kind of boring. So maybe this pressure is a 10 kPa everywhere along that line. And this is 20 kPa everywhere along that line. That's an isobar. 30 kPa, 40 kPa. True? Something like that. That's how you sketch often. You show a scalar field by putting contours, lines of constant value in it, and sketch them. True? Just as another example of a scalar, let's say this is y, this is x. Let's do a temperature field. Maybe the temperatures are, like this. Maybe everywhere here it's, I don't know, 10 degrees C, then 20 degrees C, then 30 degrees C, then 40 degrees C. We visualize a scalar field by putting lines of constant scalar value. What are those? Isotherms. Now, if I say that this is my pressure visualization of my pressure scalar field, I now do the gradient of P. What does that look like? And can I plot it on the same plot? Well, it would come back with a vector field, wouldn't it? And so at every point, it would come back with a little, let's say I want to evaluate at that point, it would come back with a vector. That vector has length and orientation. What would it look like for this example? Gradient of P. Would it be like here in that direction? Or would it be here in that direction? Or here in that direction? Or here in that direction? So A, my multiple choice, A, B, C, D. Or E, other. E is other. Ready to vote? I'm going to pause. I'm going to walk around and see you give me a vote. Let's see if I can continue on. Well, maybe I should have stepped back and say, can somebody give me an analytic expression just to make up a pressure scalar field? Just make one up. Okay? What would it look like if it looked like that? Can you do that? Would that help? It's a function, FCN, I can do a function of x and y. My brain was wanting to write x right away. But it's a function of x and y. And here, the blue lines, can you write that function of x and y that would give me something like this? Let's say at 1, at y equal to 1, and at y equal to 2, and y equal to 3, and y equal to 4, and x equal to 1, and x equal to 2, and x equal to 3, and then x equal to 4. I think you get the picture. I'm going to pause, and I want to see if you can write. All right. But somebody put over here to helpful, they said, well, the pressure at x equal to 1, y equal to 1 is 10 kPa. And the pressure at x equal to 2 and y equal to 2 is what? 20 kPa. That's true, you're evaluating at particular points. They evaluated at this point right here, and then they evaluated at that point right there. And at one point it had a value of 10 kPa, and the other value it, and say, I'm looking for the function that describes that pressure field. And I think I had 1 or 2 correct answers so far. So is it 10 times y kPa? Let me even erase that, and let's see if I can do this. Grab it and scoot it over. Okay, now the next one is the gradient of pressure. Somebody remembers, oh, I recall the gradient of F is equal to the partial of F with respect to xi plus the partial of F with respect to yj, and I left out, not enough room, partial of F with respect to z. Okay, so we apply that to this function, the partial of P with respect to xi plus the partial of P with respect to yj plus the partial of P with respect to zk. What do we get? 0i plus 10j plus 0k. And this does have units. It has units. Look at it. It's pressure per unit length. And we're staying SI, so pressure per unit length. kPa per meter. Okay? So now, which vector up there, A, B, C, D, or other, up works? B, true. So it's in the direction of I'm erasing too much, but it's hard to erase stuff. So here, here, okay. So it's B and K, so it tells you both the direction, positive I, or not positive I, positive J, right? And it tells me the rate of change of pressure if I start moving in that direction. I know all of these have some units like meters, true? Meters, 4 meters, 3 meters, 2 meters, 1 meter, right? So what does it say? That if I move straight north, if I move in the J direction, 1 meter, it'll change by, does it go up by 10 kPa? Okay, now if you get a scalar field like this, that's kind of complicated as a function of x and y. It's almost difficult. But when I get the gradient will always come back with a little vector perpendicular to those lines of constant temperature, pressure, density. And it'll be the rate of increase at that point if I start walking in that direction. And right here, maybe it's right there. I would have changed this red line like that, okay? And I'm going to ask you a question about the gradient here. That would be in that direction, true? This one's in this direction. Now focus on the magnitude of this case A, evaluated at this point, versus case B or problem, or point B, you know, the gradient evaluated at point B. Both of those have the same units, right? This x is in meters, this y is in meters, this t is in degrees C, true? Degrees C. Now the question is the rate of change for case A, the vector at A, or B greater than the other? Which one's greater, or do they have the same magnitude? All right, so I was asking the question, I'm going to erase this here, whether or not the gradient of the temperature evaluated at point A, the magnitude of it, how did it compare? Is it greater than, equal to, or less than the magnitude of the gradient of the temperature at point B? And a lot of you got that correct, right? Which one is it? Which should I erase? So the gradient of the temperature field evaluated at point A, that vector is evaluated, the magnitude then, is going to be, okay, let's take a look. What are the units of this entity? So really it's the rate of change of temperature if I move in that direction. Okay? If I look at it, I know that I have an isotherm at A, it's 10 degrees. If I know that the gradient's changing as I move, but if I just extrapolate it all the way to the next one, 10 degrees C, I would have to move how far? A greater distance. Then, if I'm at this point and I move from 30 plus 10 would be 40, I can see that it's a shorter distance. So the rate of change is faster at B. As I move in that direction at B, the temperature change is greater as I move in that direction from B. Does it matter on the curvature at A? Let's say I said I want to look at here's point A, and does it matter if the curvature is like this at A, like this at A, or like this at A? No, it's really just from A to the next one, which is, let's say, these are all 10 degrees C, and this is 20 degrees C. It's like that, a visual image of the length between them. I know that if I come up here and I evaluate it at the intermediate point, the gradient may have changed a little bit. Instead of being in this direction, it's in this direction. True? I'm not worried about that. I'm trying to get a sense of the magnitude. So we talked about the pressure as a scalar field. The gradient of the pressure is a vector field. I didn't do the derivation, did I? I ran out of time on that. All you do is go down to a little chunk of x, y, and z. All right? And you do a balance on it that says the sum of the forces on this little chunk is equal to the mass times the acceleration. What are the forces? I'll have the weight, and then I'll have the pressure on all 6 faces of the cube. And one thing about the pressure, on each face of the cube, it always pushes into the cube. The pressure is the surrounding fluid exerts a pressure on the system, which is the cube. From the bottom it pushes up, from the top it pushes down. From the back it pushes forward, from the front it pushes back. From this side it pushes back, that side pushes forward. True? So you have the weight acting down. That will be something like rho times the dx, dy, dz times gz, or gk, and it'll be in the negative k. It'll be in the negative k for this right here, for the weight. And then each one of those forces push it in the x, push it in the y, or push it in the z. And then you have the acceleration. The mass is rho, delta x, delta y, delta z. Put it all together, do the limits as delta x, delta y, delta z go to 0. You get a nice differential equation which gets the negative of the gradient of p plus rho g as a complete vector equal to ma. Is that rho a? I think it's rho a, yeah, rho a. I'm used to writing F equals ma. Now this g as a vector is 0 in the I plus 0 in the j minus g in the k. And so that's what they do, is they don't put that part of the gravitational vector in there. And you're left with the equation gradient of p plus rho gk equal to minus rho a. So you see how they handle the minus signs, but that's the equation that's in the textbook. Now let's take a look at this problem. I have a jug of water, a tank of water, and I just let it free fall. So the liquid is free falling in the gravitational field, free fall. Does anybody know the rate at which it will accelerate, neglecting wind, drag, and all that? What's the rate at which it will accelerate as it free falls? 9.81 meters per second squared, 32.2 foot per second squared. What will be the pressure difference between the top and the bottom of the tank of water in free fall? Will there be a difference in the pressure between P2 and P1? Yes. Now let's make it stationary. It's not free falling, but it's still in a gravitational field, true? It's still in a gravitational field. If it's in a gravitational field and it's stationary, is there a difference between the pressure at P1 and the pressure at P2? P2 is higher. Why is it higher? Because of the hydrostatic head. Now let's put it on an elevator. Let's put it on an elevator that's accelerating upward. It's still in a gravitational field. Will the pressure at the bottom of that tank be greater than the pressure at the top of the tank? It'll be much greater even than if the tank was at rest. Now, what happens if I take the same tank, I'm not accelerating or decelerating or free falling in the vertical, I am having it accelerate horizontally. You put it in a car. Somebody's holding it in the front seat. The light turns green and you romp on it with constant acceleration for a while. What does the water do in the tank? It's going to slosh up like that because you're accelerating in the positive x with a positive acceleration. True? As soon as they stomp on the brakes, you have a significant deceleration. It'll slosh back. Once you're doing 60 miles an hour, constant speed, it's back to just being flat. But while you're accelerating, it's like it has gravity pulling it down. True. You have acceleration to the right. True. You can think of this, either kind of sketch a force diagram. There'd be like a force in the opposite direction of the acceleration. Well, I know if it's accelerating, I'll just put ma as some sort of equivalent force, put it over here, some of the f's. Now I'm back to statics. Hey, I like that. What is the name in dynamics they use for this force? Like imaginary force or inertial force or something like that. That's one way to handle or solve these problems. So then you have the weight coming down. So you have like a force pushing on the object that way, a resultant force. True? Okay. And this sloshing angle, theta, is the same angle as that angle right there, theta. And so you have similar triangles, theta, G down, AX for that side. And so now I can get a relationship between the angle of the tank, the surface angle of the tank. The tangent of the angle of the tank is equal to AX over G. Now, what about the pressure lines? Well, you'll have a line of constant pressure. First of all, the free surface is a line of constant pressure. True. And then the lines of constant pressure won't be horizontal anymore. They'll be slightly tilted by the angle theta. True? So if you said, okay, I want an analytic expression for the pressure field where down at the origin at x, z, so this is the x coordinate, the z coordinate, that's the location 0, the origin. We could talk about the pressure at the origin. Is this a nice analytic expression that you could also, you're a devilish little guy, right? You could be accelerating it horizontally, and in addition to the weight and the gravitational field, you could also put it on an elevator. In this case, what was a sub z as I was describing it, 0? Just purely horizontal, a sub x is that. But if you just say, okay, this equation works for both a sub x 0 and a sub z non-zero as well as the other. Another problem, we have a cylinder container, and it's now rotating with the rotational rate omega. What would be good units on omega? Radians per second. Around the center of that cylinder, okay? Intuitively, the water is going to be flung out to the sides, and you'll have a higher, the surface, a free surface, will be higher at the sides and lowest right in the middle. What do we do for this case? Go back to our general differential equation, which was written gradient of P plus rho g k, that's a vector, this is a vector equation, equal to rho with the minus sign. Just the fluid is being rotated. For every little chunk of fluid right here, what's its acceleration? Well, it's feeling it weight down. That's being accounted for right there. But it's also feeling a push from the fluid behind it to go to the middle. It's constantly being accelerated toward the middle. That's exerting a force on the object, accelerating it toward the middle where you're pivoting or rotating the object around the string. Does anybody recall, if I have a string, the object mass m, its instantaneous radius of curvature, what is the acceleration equal to? It's equal to omega squared kappa r, the radius. So how can we express this differential equation in the coordinate system of preferences I, j, k? Cartesian. But in this problem, what type of coordinate system would we like to use? Theta, r, and z. R, theta, z. So z is still lined up with the x, the z or the k direction, right? Because maybe I should have put x, y, z, and then you have r, theta, z. And do you recall the little unit vectors? Let's say at this point right here, its unit vector is e sub theta, e sub r, and E sub z, it's hard to show it going up, E sub z going up. But in the polar coordinate system, you have to have some little unit vector that's going straight out in the radius. And then perpendicular to that is E theta. E hat theta, E hat r, okay. Was that out of the Hibbler textbook for dynamics?
Yeah.
What was the gradient of pressure in this other coordinate system? So what is going to be that acceleration? Something E sub r plus something E sub theta plus something E sub z. It's not free falling. It's not on an elevator going up or down. So what is this term? 0. Okay. So now I have a choice. Is it going to be a non-zero E sub r? Or a non-zero E sub theta? Or, all right. So I think the consensus of the class was which one is 0? A is 0? The other consensus of the class was that B is 0. There we go. So there we go. We finally got it. All right. So what happens is you take this vector equation and you bust it into 3 scalar equations like I, J, K, but here it would be in the E sub r direction, E sub theta direction, whoops, E sub theta, I can write that, E sub theta, and E of z direction, true? So you get up to, from the one vector equation, you get up to 3 scalar equations. Because of the rotation is constant, this equation is 0 is equal to 0. Blase. But what happens with the E sub z, maybe that one's the easiest for you to understand, is that you get the rate of change of pressure in the z direction plus rho g is equal to 0. We're not accelerating it in the z. Okay, I'm not on an elevator. So this component was 0 on the EZ. True? All right. And the hardest one, you have to go back and do a little work, but you pick up that rho r omega squared equals to the partial of p with respect to z, not z, the partial of p with respect to r. What is this lowercase r right here? It's the coordinate r. Should that be cap r? Should this be cap r? No, it should be lowercase r. Essentially, the chunk of fluid that's further out, r is increasing. R, lowercase r goes between 0 and cap r. The further out it goes, the more inward directed acceleration it needs to feel from the pressure field to keep it in solid body rotation. Now, this is an ODE, this is an ODE. In the interest of time, since I'm out of time, you can get the pressure field. The pressure is a function of R and Z. The pressure field is some P naught. What would be P naught? Right here is the origin, true, plus 1/2 rho omega squared R squared. Solve this equation and you'll pick up R squared with the 1/2, right? Plus, I ran out of room, minus, sorry, because our Z is increasing, minus rho G Z, there it is. You can do some manipulation and you can get another equation and another equation. I encourage you to look at those equations. I do have 5 minutes left to this class, okay? So, what happens the next time we meet? There's a test. We already talked about how to study for the test. You have an equation sheet for the test. These equations are out of chapter 3 for your test. These last 2, I know we just blew through pretty fast, but that's applicable for something that's rotating. Constant omega. Be able to solve those problems either with the solid cylinder, or if I have a manometer like this, or U-tube, yeah, and then I have an axis and I rotate at constant omega around that axis, the fluid level will shift downward and upward. Be able to solve those type of problems, okay?